Today's episode dives into three very different but equally provocative frontiers in AI: an agentic reinforcement learning system that learns how to design better heuristics with fewer costly evaluations, a diffusion-based attack that reveals how realistic driving scene changes can break online map construction, and a quantization-triggered backdoor that turns deployment compression into a security risk. Together, these papers show AI becoming more autonomous, more capable, and more vulnerable all at once. Stay with us as we unpack the ideas reshaping how intelligent systems are built, attacked, and defended. Let's explore the first paper, AHD Agent, Agentic Reinforcement Learning for Automatic Heuristic Design. AHD Agent proposes a tool-integrated, multi-turn reinforcement learning framework for automatic heuristic design, replacing fixed workflow systems such as EOH, ReEvo, and MCTS AHD that treat the LLM as a passive code generator. The core idea is to let the model actively choose between generating a heuristic and calling diagnostic tools, specifically an instance analysis tool for design set structure and an AST novelty analyzer for code structure novelty, both restricted to training instances so validation leakage is avoided. The policy is trained with GRPO on a synthesized RL environment built from 4,000 prompts across 4 domains: TSP constructive, CVRP constructive, TSP ACO, and CVRP ACO, using a compact Qwen34B Instruct 2507 backbone. Across 8 evaluation settings spanning routing, ACO, and cost-aware Bayesian optimization, the trained 4B agent matches or beats much larger LLM baselines while using far fewer evaluator calls, typically 1115 versus 100. On held-out OP-ACO, OVRP constructive, MKP-ACO, and CAF, it remains strong. For example, it reaches a 12.837% gap on OP-ACO at n equals 200 with only 13.6 evaluations and a 1.79% average gap on 12 Bayesian optimization functions with 14.2 evaluations. Outperforming handcrafted acquisition rules like EI-cool at 2.92%, the paper's main novelty is not better prompting, but an agentic policy that learns when to inspect instance structure, when to revise code more radically, and when to stop, which yields both higher quality and substantially lower search cost. Let's explore the second paper, Systematic Discovery of Semantic Attacks in Online Map Construction Through Conditional Diffusion. This paper introduces Mirage, a latent space semantic attack framework for online HD map construction that replaces pixel space perturbations with conditional diffusion search over realistic driving scene variations. Using Magic Drive, a stable diffusion 1.5 based multi-view generator conditioned by ControlNet and steered with clip direction loss, Mirage first inverts clean new scene surround view images into a diffusion latent, then performs projected gradient descent in latent space to discover plausible changes such as shadows or wet asphalt that preserve road topology while degrading MapTR's BEV map predictions. On new scenes, Mirage suppresses 57.7% of road boundary detections and is the only method that reliably injects fictitious boundaries, adding 1.88 detections per scene. Those injections produce a 33% false stop rate and up to 52% off-road rate under an A times planner. Standard preprocessing defenses tuned for high-frequency noise, including JPEG compression, median filtering, and diffpure, recover 81% of pixel PGD's effect, but only 36% of Mirage's, exposing a gap between pixel and semantic robustness. Realism is quantified with 2 independent VLM judges, InternVL 3, 8B, and Gemma 4E 4B, which rate Mirage samples as realistic 79.9.84.4% of the time, close to clean new scenes at 96.5 and 98.5%, and far above AdVPatch at 0.9%. The attack also transfers to the black box VAD planner, increasing trajectory deviation relative to PGD and AdVPatch. A chalk-based physical proof of concept on a closed road reproduces Mirage's qualitative failure direction, showing the vulnerabilities survive the digital to physical gap. Let's explore the third paper, Widening the Gap Exploiting LLM Quantization via Outlier Injection. This paper shows that LLM quantization can be exploited as a trigger for dormant backdoors even in practical optimization-based schemes. The authors introduce an outlier injection attack that plants one large outlier per quantization group, typically in the FFN upproj matrix, so that methods such as GPTQ, AWQ, HQQ, SynQ, AutoRound, and GGUF iQuant collapse the remaining weights in that group to 0. They combine this with a 4-stage dual objective fine-tuning pipeline. 0 initialize a switching block. Train a split behavior where the BF16 model stays benign while the future quantized proxy becomes malicious. Inject outliers, then refine against a quantized proxy that explicitly zeroes non-outlier weights. Across Qwen2, 5, 7, B. Instruct, Llama 3, 1, 8, B. Instruct, and Mistral 7, B. Instruct, V. 0, 3. The attack raises post-quantization attack success rates to above 90% in most cases, including 94.7% on NF4, 95.7% on GPTQ 4-bit, and 95% on AWQ in the jailbreak setting, while the BF16 attack models remain near benign, often below 5% ASR. Utility degradation is limited. Average benchmark retention stays at 98.8% for Qwen2, 5, 95.9% for Llama 3, 1, and 93.8% for Mistral. The paper's novelty is that this is the first quantization-conditioned attack to generalize across calibration-based and calibration-free quantizers, defeating prior noise-based defenses and expanding the threat model from simple, zero-shot quantization to the methods most commonly used in deployment. That's a wrap on today's AI paper highlights. Thanks for watching.